Um, all right, let me know if you don't see my presentation. Otherwise, uh, good morning, good afternoon, good evening, wherever you're based. My name is Zhibai. I am a DeFi strategist at VolumeFi. As a company, we are mostly focused on cross-chain, blockchain transactions and messaging. As such, we do a lot of systematic DeFi analysis. Today, I'm very happy to join PyChain and talk about some analysis that I have done in terms of analyzing crypto market microstructure. And also, I'll talk about how to do these things in Python. All right, let's kick it off. I would say, before joining crypto, I actually had been a quant in traditional finance for several years. So in traditional finance, market microstructure is a fairly well-studied topic. It is pretty often used both by academics and practitioners. So I think as a starter, let me give you an introduction about microstructure, what it is, what is used to. So in traditional finance, market microstructure is really just the study of the microscopic dynamics of exchange activities. So predominantly, what happens on an exchange is, people trade, so activities actually go beyond that. Behind behind the scene, market makers have to very actively manage their limit orders. And so having said that, you probably have guessed that the main playground for market microstructure is the electronic trading exchanges, especially those with very large volume and high turnover. So for these exchanges, normally they have a centralized limit order book, and they have a matching engine that constantly pairs up a bid and ask. So what market microstructure tries to do is it basically quantitatively measures the terminologies that a lot of traders talk about, such as liquidity, order imbalance, bid-ask spread, order toxicity, price impact, etc. So these things obviously are of significant importance, but the study of market microstructure really tries to come up with formulas and statistical tools to measure and analyze each of these things that I just mentioned. So that brings to sort of the main challenges for this in this area. So first of all, it is by its nature a big data problem. So this is the where you have the largest data sets in finance. Basically, if you dive into trade data and you go as granular as possible, we're talking about individual transactions, and beyond that, we also have snapshots of the entire order book. So that's a very large amount of data. And also, in order to process and take action on these data, you have to be moving very fast. So that's high speed in terms of computing and also communication. There's also relatively complex algorithms involved in order to process and analyze the data set properly. So that all basically sort of adds up to the operation overhead. And then you might ask, for those who are not familiar with microstructure, what is it mostly used for? Well, so it's predominantly used by market makers slash high frequency trading firms. So their end goal is basically they need to very actively manage their positions and their orders, their open orders, such that they want to avoid toxic orders as much as possible, and also be able to provide the bid-ask spread as tight as possible, so they can generate a lot of trades. For liquidity takers, namely people who are not market making, but they would like to take positions, it is also useful because when it comes down to execute a trade, so most likely you're trading against a market maker, and if your order is sizable, then you do want to have a let's say proprietary strategy to enter your position, such that you can optimize the execution. And then lastly, there's a lot of quantitative strategies use microstructure variables to come up with trading signals, such as if the liquidity measure goes above a certain threshold, that turns out to be a buy order for certain instruments, things like that. So these are the main applications for microstructure in traditional finance. And as I will talk about in a few minutes, it's also all these things can be directly applied to crypto trading. So before I jump to the crypto market, so in terms of the overall toolkits, so you have several things. So you need, if you are doing things fairly fast, you're market making, high frequency trading, then you got to use a low latency language to process the data in real time. So we're talking C++ and Java. But also for statistical analysis and things that are latency wise is not an issue. There's a lot of Python usage. So obviously we want to talk about Python in this talk, and also the following talks as well. So API wise, communicating with data vendors, the exchange. And lastly, you need to have a database to handle historic data, real-time data, et cetera, et cetera. All right. So when we talk about switching to crypto market, so it's not that different from traditional finance when we look at centralized exchanges such as Binance. And I guess given what has happened, what has transpired in the past week, let's just stick with Binance. So centralized exchanges in crypto operate in a very similar fashion compared to their traditional finance counterparts. So they run a centralized limit order book, they have a matching engine, and obviously it's run by a single entity, and it's fast. Most of the trades happen there are off-chain, so they're not taking place on a blockchain. So in that case, they still, so basically the players, the types of players are also very similar to traditional finance. So you have your regular your sort of market makers, active market makers that actively providing limit orders and then managing their positions. Now, the difference would come in when you look at decentralized exchanges, which exclusively exist in crypto. So they are smart contracts implemented on blockchains, And blockchains are run by multiple agents, so it's fully decentralized. The trades of decentralized exchanges all happen on chain, so they are bounded by the each blockchain's block time. So they're relatively slower, and there's no traditional sense market maker in this case. It's just the smart contract. The market making strategies are pretty much fully on chain. So that's kind of different. For the most part of the remaining of this talk, I'll just stick with centralized exchanges, but if time allows, I'll briefly talk about how to use the same methodology in the decentralized exchange case. All right, so just to kind of show you some sample data to give you an easier way to visualize things and think about what we're trying to do. So assuming that we are we have market data, and the name of the game is now we're in crypto, and we're looking at crypto centralized exchange market data, and we would like to build microstructure variables on top of these, and try to analyze them, use them for trading purposes. So we're talking about a data table that looks more or less like this one that I'm sharing. So if you aggregate the data on a 1 minute level, then you can have the very regular open, high, low, close, and volume fields. So really, the study of microstructure is saying that look at each bar. Can you use the information from that bar and the information before that bar to come up with a number for that bar, such that the number quantitatively defines liquidity, order imbalance, et cetera, et cetera. And so taking it from there, I'm going to introduce 4 very well studied and very popular market microstructure variables in traditional finance. Walk you through their definition and walk you through how to use them. So the first one is called role measure. This is actually, so it is invented by a professor of finance. Last name is Rowe. This actually was invented in the 80s, and but it has been sort of used in different times. So initially, it was designed for daily market data, but now it could be used in pretty much any time frame. So role measure really is a measure for autocorrelation of returns. So in the crypto's case, so we're talking about a token's return autocorrelation. And autocorrelation in layman's term is just the measure of a trend. So if you see, let's say, Bitcoin, the price is sort of just wiggling, it goes up and down a little bit, and then it doesn't really, go up a lot or go down a lot. In that case, this measure would come up low. On the other hand, if Bitcoin is rallying, just continuously going up and up and up, then this measure will become higher in value. So without really getting into the details, it is computed by taking the price change series of a token and shift it, and then calculate the covariance of the 2 series. This is a pretty standard autocorrelation calculation. And moving on to the second one. So Kyle's lambda is invented by a professor, last name Kyle, also in the 80s, which is defined to measure price impact by signed volume, or simply put, price impact. So the calculation mostly is done by taking the price change of a certain period and then divide it by signed volume, such that you can basically, so the interpretation here is that, let's say you are a liquidity taker and you have a large position that you want to enter. You know, let's say you want to buy a lot of ether. You know, when you buy, you're actually dragging the price up, right? So this measure basically tells you, for like you want to buy 1 ether every time. If you look at the historic numbers, how much price in terms of price change is driving the token in that direction. And therefore it measures price impact. If you see this number become very large in magnitude, it basically says the price impact is significant, and therefore you want to trade less if you want to minimize your slippage. Third one is called Amihu measure. This is invented in the early 2000s. Is a measure of pure market liquidity or illiquidity. All right, so it basically is the absolute value of returns of a token, or in traditional finance, a security, divided by the price volume sum over the same period. And therefore, the interpretation is when the market liquidity is good, this measure tends to be small. And whenever you see this number spikes, that's when the market liquidity is drying up. Because when the market liquidity is very dry, there's no liquidity, then even just with a very small volume, the return will be very amplified. Now, lastly, so it's called volume synchronized probability of informed trading, or basically VPIN. This is a measure for order imbalance. So, I'm gonna leaving the details out of this. So the name of the game is really, we would like to use these 4 measures, and we would like to use Python to generate these measures for crypto. We could use Python to generate these measures. For instance, giving you a sample code here. So using pandas, which is a very popular data manipulation library, you can very easily generate write a function that takes 2 pandas series in and returns a whole series of Amihu in a time series fashion. So looking at the same database, once you pass on the function I showed you, we'll get this column. So that's therefore we get a way to basically measure the illiquidity. And before I finish, so showing you how this is sort of how liquidity measured by Amihu looks like. And this is Bitcoin. I actually took the price from last year, 2021. And you'll see, so that's why the price was so high, close to, well, it was the all-time high. And you see whenever, so, I think through April and June, there's a illiquid period. And because you see overall, the Amihu measure was high. And you see these spikes when there's very large, usually one directional movements for the token. And I'm running out of time, but basically I think that the takeaway is you can use Python and crypto data to generate these market microstructure variables and use them to, circling all the way back, use them to measure illiquidity, order imbalance, bid-ask spread, order toxicity, price impact, and all the other important market variables quantitatively. Thank you.
Thanks for that, Zhibai. Guys, I know there was an issue with the live stream. There'll be a raw recording up in 30 minutes here, and it'd be great if you guys can all meet in the face-to-face link which we put into the Discord there on the track to discuss further with Zhang if you'd like. It's been a pleasure.
Thank you. My pleasure too.
Thank you.